Yep.
Hello. Okay. Hello. Welcome to the last session of the day. Our first speaker will be Filip, who will tell us about infinitesimal models of algebraic theories.
Thank you very much. Okay, I think everyone can hear me, and I hope that on the online people can hear me too. So thank you very much for coming, and thank you very much to the organizers to, first of all, organize this event, of course, and allowing me to speak. I would also like to thank the Crawford Foundation for generally supporting part of this research. All right, let's get going. So there are kind of three parts to this talk. In the first two, I'm going to be focusing on the applications of infinitesimal models. We will be starting with the question, what is actually an infinitesimally affine space, which was the question that I asked and was pursuing, and that kind of motivated the whole thing. From there on, it's kind of quite a small jump to realize, oh, I can actually do that for algebraic theories. But then the question is, well, what can you do then? If you have this kind of more general notion, what can you do with that? So we'll be looking at Lie groups, applications of that to Lie groups. And then I kind of want to forget about all that infinitesimal business. And I want to talk about the category of infinitesimal affine, infinitesimal models of algebraic theories, because it's kind of nice, and I think it is an interesting category to look at as an extension of the category of algebraic models. So let's get started. The intuition that's been around like literally for forever, since people started thinking about like curved spaces, was that somehow a manifold should be an infinitesimally affine space. And, you know, I mean, we're familiar from this. We look around, we're living on a curved surface. But really, when we're kind of close, then it appears flat. Of course, it is not really flat. And if we want to kind of make it precise that it should be flat, then we would need to do something like we would need to zoom it infinitely close, right? Like any finite level is not sufficient because curvature is not going to disappear. You would need to go infinitely close. Well, that's what our predecessors did, at least in their intuition. They had a few issues with these things that they called infinitesimals, so I've kind of denoted them here with dx and dy, because they were kind of nice, they were really useful, but they were also a bit annoying to deal with, respectively. They were annoying for people to understand whether that argument is actually self-consistent or not, because you either introduced them and you calculated with them, and when you didn't need them, then you just kind of got rid of them. This is something that physicists and engineers like to do until today. Their justification is, of course, well, I know I'm reasoning here, and if I get something that I can apply in reality, then I don't care how I arrive there. But maybe as mathematicians, we do feel uncomfortable, and we want to change that. There are actually two constructions that we can see happening here. So first of all, we have this kind of vector addition, and these vectors, this is what would be the tangent vectors, but we can also look at points, right? So I can also look at points, and I can form affine combination of points, which we see here. And that's actually what we're going to be doing, right? At least in this lecture. We're not going to be looking at tangent vectors at all. We're going to be looking at points. And this is only possible in synthetic differential geometry. So infinitesimals, how to model them? This was something that people were struggling with for several hundred years. Berkeley called them lovely the ghost of departed quantities. Then we had Abraham Robinson, I think in the 1940s, don't nail me on the date, where he came up with the idea, oh, if I'm looking at a non-Archimedean field, then I can actually, construct one, really nice one, where I can transfer all the good stuff from the real numbers over, and I'll get like infinitely big numbers and infinitely small numbers if I divide by an infinitely big number, and that is become non-standard analysis, which is also reasonably popular and getting more and more popular. And then we have synthetic differential geometry, which comes from Lovir. So Lovir's attempt to kind of develop a categorical framework for doing physics, and that of course requires dynamics. And he came from the side of algebraic geometry and looking at it from the point of view of categories. And most of the work in synthetic differential geometry and its applications has been developed by Anders Koch. And Anders Koch and also me kind of following his shoe steps, we're actually moving away from just looking at it as Lovere did from the categorical point of view, but using what is so-called naive synthetic differential geometry. So we're going to be sticking with synthetic differential geometry rather than non-standard analysis, and the reason for that is quite simple, because synthetic differential geometry actually is closer to, or like it's more suited, the model of the infinitesimals is more suited to reflect our intuition in geometry that we're using, whereas non-standard analysis is better for analysis and analyzing infinitesimal arguments there. So how does synthetic differential geometry model infinitesimals? Quite quickly, it's nilpotence. So we're assuming an R algebra R, and we're assuming it has like sufficiently many nilpotents, and nilpotence just means that for some finite power, that thing will eventually get 0. Now, you might wonder, why would I want to do that? Kind of what's the point modeling an infinitesimal quantity with a nilpotent? Kind of in a nutshell, and I will kind of show an example on the next slide. If I have a map from my smooth space M, and I'm kind of believing, kind of like the engineers and the physicists do, well, whenever you have a map, actually you're looking at a Taylor series. Okay, so everything has a Taylor series. It's a beautiful world. And well, what happens if you plug in an nilpotent into a Taylor series? Well, it will automatically truncate, and you will get a polynomial. And that is the whole idea behind the so-called Koch-Lovere axioms, which kind of formalize, okay, what do we understand at infinitesimal spaces? How do we define what that is? Again, don't bother about the details at the moment. It's just kind of a little infinitely small space around P, but it has a geometry. And this geometry is reflected in the polynomial M, in the polynomial map that the function becomes when you restrict it to this space. So here we have a one-dimensional example. We call then this R algebra, also called R, of line type, when it satisfies all these Koch-Lovere axioms. And here there are two examples. So what you can see is like my smooth function f. And this smooth function f can now be evaluated at a point, and then I can kind of restrict in the green region. The green region, this would be kind of the first order infinitesimal, so they squared to 0. And I can see that the Koch-Lovere axiom tells me, okay, then it becomes a lie, okay? So when I restrict this function to first order infinitesimals, it is a line or an affine function. And if I now say, okay, but what if I kind of go the next step and look at second order, so make the thing bigger, the infinitesimal spaces I'm looking at, well, then the Koch-Lovere axiom will tell you that it will be uniquely a quadratic polynomial. And these B1s and B2s, they can then, of course, be replaced and used to define derivatives. So this is an example of the kind of general idea, but it generalizes to higher dimensions, yada, yada, yada. But let's leave that. It's kind of not a so important detail for us at the moment. Okay, so now you might wonder, like, right, but where is the category theory going on? And so far I have not mentioned any. Well, as you noticed, I've essentially claimed with the Koch-Lovere axioms that every function is smooth, that everything is differentiable, and you must say, oh, no, okay, that might lead me into some trouble. And this is where category theory, or respectively topos theory and categorical logic, come to save us. So when we work in a naive differential geometry, we're of course working on the syntactical side, and we can do that because there is categorical logic which tells us, yes, you have models for that. These models are called well-adapted models. So this is a full embedding of the category manifold into some Grothendieck topos, and this has particular properties. So, for example, it preserves, like, in a sense, it preserves and translates all the good stuff, okay, as that's what it should be translating. So, for example, it maps the reals to this R algebra of line type, so or smooth line, or model of a smooth line. It preserves also transversal pullbacks, that is important, and it maps open covers to jointly epimorphic families, so this is how we get like all the manifolds in. And yeah, as that's it, and then you can prove that it also translates derivatives, everything just done exactly how it should be. And that's amazing because you can then go and simply forget about it. All right, so it's kind of running in the background, the machinery is working, and we can continue to develop our theory naively. Of course, we have to pay attention if we are in topos. It's never a Boolean topos. The model for synthetic differential geometry would be the trivial ring. If we look at the Boolean topos, so it is hiding logic, and that means we have to be careful with our reasoning here. So no law of excluded middle. Yeah, but in general, we do not use it that much anyway. So especially when you analyze arguments of physicists and engineers, like the law of excluded middle doesn't necessarily pop up. So actually, one doesn't need to be too worried about that. Okay, so now how do we make the idea precise how a space becomes an infinitesimally affine space? Right, we now know what infinitesimals are, and that means we also know that like when to speak about infinitely close points, right? So now I can look at a finite family of infinitely close points, and I can just do affine combinations of them. Right, so this is what we see on the slide. So basically, I have a notion of infinitely close points. I have affine combinations in my R algebra, and I can simply do affine combinations in the space itself, as we've seen here. Right, so let's make that precise. Let's model that stuff. So first of all, we want to axiomatize what it means to be infinitely close. That is what I call an I structure, infinitesimal structure. Yeah, I decided to do Steve Jobs on this one because like writing out infinitesimal every single time just gets tedious. And what is that? Well, essentially you say not all points, like no all tuples of points are infinitely close, but I have to specify which ones are infinitely close. Okay, so of course each point is its own neighbor, and then whenever I have a family of infinitely close points, so this is this axiom 2 here, then well, I can kind of reorder, I can double them, I can restrict them, I will always get families of infinitely close points. So hopefully that kind of makes sense. So nothing big and extraordinary here, all the obvious things that you would want to write down. So let's look at some examples of infinitesimal structures. So if I'm kind of taking an n-dimensional vector space over R, then I can construct a bunch of such infinitesimal structures. A0, this would be the discrete I structure, where of course only the point is its own infinitesimal neighbor, so there is nothing else. A1 would be first order neighbors, A2 second order neighbors, and so on. Then I can join them all up, and then I'll get A infinity, so kind of arbitrary, infinitely neighbors of arbitrary degree. And of course, I can assume that everything is an infinitesimal neighbor, and then I get the discrete I structure. Now, there is one that's kind of standing out a little bit, which is called, or I call it the Neal square I structure, and that is the infinitesimal structure that has been used by Anders Koch literally in all of his work. So he has not been, I mean, he hasn't singled out the idea of a structure because this is a bit alien to SDG. Like we want that everything is natural in SDG, so we do not want to think in terms of structure, but it turns out that this is actually a good idea also in SDG to think in terms of structure, and we will see later why. So this Neal square I structure, kind of, you see that in the second line, here, because we are kind of in higher dimensions, we need to explain what does it mean squaring a vector. Well, it means that if you put that into any quadratic form, then this is just going to kill it. And that is true for any quadratic form. Whereas first order means that any second order occurrence will cancel out. This is a bit subtle. What Neal square infinitesimals allow us to do is, for example, to have determinants. So it is, if I have like, for example, a triangle of mutual infinitesimal neighbors, which would be Neal square, then I have an infinitesimal volume or area, so to speak, that is not provably equal to 0. Okay, so that is the difference. In first order, everything vanishes. Like everything, what's more than everything second order up is 0. So therefore, the Neal square infinitesimals kind of always stand out, or sorry, the Neal square I structure always stands out a little bit. Right, so having done that, it's actually quite simple to now move on to define what an infinitesimally affine space is. We say, right, instead of having these affine combinations acting on all tuples of points, we restrict it to the infinitesimal structure. And what is very important, of course, if I'm restricting, if I'm making a partial operation, is that these things are compatible. And for them to be compatible, we need this so-called neighborhood axioms, which essentially says, okay, you're starting with an infinitesimal neighborhood, and you form like affine combinations of all of them, like whatever affine combination, you'll stay in an infinitesimal neighborhood. You're not going to leave it. So again, I hope that this is quite natural. And then we have the usual stuff, right? So I have associativity, and I have projections. When I'm just using the 0, 1, 0, 0 affine combinations, then I will just reproduce these points. So then, of course, kind of double checking that we're on the right track. There are two theorems here. One proven by Anders Koch himself, even though he's, of course, not been using this terminology and this theory. So he kind of proved that, like he proved essentially the thing, but he hasn't used these terms. That every formal manifold is an infinitesimal affine space on the Néel square I structure, and all maps between manifolds are infinitesimally affine maps, which means the obvious thing, preserves the I structure and affine combinations. And then a result from me, which actually realized, or I was asking, well, what's happening if I'm going into second order and higher? And there it turns out that, first of all, you need something which is called a symmetric affine connection. And if you have a symmetric affine connection on a manifold, it's exactly, it's equivalent to stating that you have an infinitesimally affine structure on the second order infinitesimal, like, yeah, on the second order I structure. Okay, so that is a really nice pointer that kind of tells us, okay, so like all these constructions, this additional data that we kind of take in differential geometry, actually is reflected in the infinitesimal algebra, all right? So it also gives a beautiful interpretation to what it means to have an affine connection at an infinitesimal level is basically, well, you just add points. That's what it is. Right, so now I said, let's look at how to kind of level it up. The first observation, which is, yeah, I mean, if you dig around a little bit, then you notice, well, what is this collection of affine combinations really? Well, they form a clone. Now I'm going to spare you the kind of formal definition what that is. Let me just kind of give you a few examples. I mean, maybe I can throw in a word for those of you who are familiar with operats, and this would be a Cartesian operat. So this is an equivalent way of looking at a clone. Clone comes from universal algebra and is essentially the algebraic structure to deal with substitution of terms. So let's have a look at a few examples. So here, when I'm kind of forming affine combinations of affine combinations, that is exactly that substitution of terms that I'm talking about, and that kind of encodes the whole theory of affine combinations, of affine spaces. And I can do the same thing, surprise, surprise, for linear combinations, right, if it works for affine. So that would give me an infinitesimal vector space when I'm kind of jumping ahead and using that as a definition. Or, and this will be another example relevant for this talk, if I'm looking at groups. Okay, so there I'm just taking the group of, the free group of n generators, and this operation is just substitution of terms, and that actually works for any algebraic theory. I mean, we've already heard what algebraic theories are on Monday. This one is even simpler because it's single sorted. So you can basically look at the term algebra, quotient out the necessary relations given by the equations of the algebraic theory, have substitutions, and that is your clone or abstract clone of this algebraic theory. So you can turn any algebraic theory into its corresponding clone and vice versa, so they're equivalent notions. Now, if I got that, then again, it's, I mean, I probably shouldn't even put that definition down when we were looking and see what all these indices mean. Like, you can freely ignore it by thinking about, okay, before we had these affine combinations being applied to points, well, now we have the terms of the theory, so all the derived operations, and we throw in the points, and when we compose these operations and apply, and then stuck the points is the same as we would have stuck the points and then applied the operations later. So that's all that it says. Okay, the key thing here, of course, again, the neighborhood axiom, everything else is the same as if I would be writing down an algebraic theory. The neighborhood axiom is the one that makes it an infinitesimal model. And again, the same idea. If you start with a neighborhood, you remain in the neighborhood. That's what it says. Now, this is quite nice. It's also quite nice to build the theory because, like, clones have the advantage that they do not depend on the presentation of the algebraic theory. So which axiomatic system you're using, you can use anything. It yields the same clone. However, if you were now to go and take this definition and want to prove that, for example, oh, is this an infinitesimal group, then that would be quite cumbersome. So there is a version that I prefer to use, I call it for the working mathematician, which actually utilizes logic rather than kind of universal algebra. We can do something that's called like an infinitesimalization. Again, can be formalized. We do not have to worry about that in particular. I'll just give an example. If I want to axiomatize an infinitesimal group. So I'm starting with a theory of groups and I'm turning it into the infinitesimal version. Then I essentially need to encode the neighborhood axiom because we learned the neighborhood axiom. That is the key thing that is very different. Okay, so and here you can see how that works. We have all the generating operations, which is the multiplication and the inverses, and we just need to make sure that whenever we kind of operate on a neighborhood, then we can stay in the neighborhood, and it is sufficient to do that for these generating operations only. Okay, and the rest is, well, the axioms of a group. So now there's something particular happens if I introduce constants, because affine spaces, they do not have constants. But a group, of course, or a vector space has a constant, namely the neutral element. That has, when we look at the neighborhood axiom, that of course means I have some restrictions going on here. Whenever I'm looking at an infinitesimal group, so for example, I'm taking a Lie group and I want to study its infinitesimal subgroups, well, that means I'm looking at the neighborhood of the neutral element. So everything has to be a neighbor of the constant. So therefore, whenever I have constants, the whole thing becomes infinitely small. Okay, the M stands for monad. I'm trying to avoid that term here because like people will be confused. Just pointing out why are we calling that a monad is because of Leibniz, and because Leibniz, who came up, or like was the main drive for the theory of infinitesimals, he was calling these things, or like not these things, but corresponding things, monads, is part of his philosophy. So therefore, this is called like a monad, but never mind, I'll try to avoid it. Okay, so I promised that actually the different infinitesimal structures do matter that we have. So if you look at the first order and the second order, then infinitesimal structures, then you will see, okay, so this infinitesimal neighborhood of the identity becomes an infinitesimal group. However, for the Néel square I structure, actually it fails. Okay, so this is the first time that the Néel square I structure doesn't deliver, and we see, okay, it really matters, the things that you are looking at. So I think another nice thing to show is how differential geometry actually translates into infinitesimal algebra and vice versa. So what you have here are the kind of constructions that we're doing in algebra, like group theory, and also in differential geometry, and you can kind of see, oh, they happen to be equal. Okay, and then how that actually looks like in the first order and the second order structure, and then if there is a bracket like chart, then this is how it would look like in a chart if I'm, because again, a Lie group is a manifold, so it's a group object in the category of manifolds. I kind of only focus on a few of them which are interesting. So when you look at the group multiplication, for example, then you see, let's move here. When you look at the group multiplication, then you see in first order, this is just addition. This is something that we're also familiar with from formal groups. And when I'm looking at it in second order, then I'm getting the Campbell-Hausdorff and Baker formula, at least up to second order. Okay, and yes, that bracket is the Lie bracket of points from which I can use to actually construct a Lie bracket of tangent vectors. And it so happens that if I'm using infinitesimal algebra, then for any Lie group, this Lie bracket of points is actually the same thing as the matrix commutator, right? If I would be looking at matrix Lie groups, then the Lie bracket is the matrix commutator. That is actually true in second order, at least for all Lie groups, okay, for all infinitesimal subgroups of Lie groups. Yeah, something that we're already familiar with from SDG is that actually the Lie bracket is also the group commutator. So yeah, I mean, you can look at that inversion is just point reflection at the identity. I hope kind of that shows a few examples, like how first of all, like group theory, like really connects to differential geometry. And those of you who maybe have done differential geometry and have seen how you construct left invariant, right invariant connections and yada, 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 all this stuff using classical differential geometry will hopefully appreciate the beauty of this and the simplicity and the very clear link that it has with what we know from algebra. Okay, it just happens to become polynomial in the sense either linear or quadratic if we restrict to infinitesimals. Right, so that's kind of Lie groups, but we had this one result proven by me where we said, okay, we had these affine connections on a manifold, and that kind of corresponded to infinitesimally affine structures. And if you read that assertion carefully, it said symmetric affine connections. So next question would be, well, what happens if you have a non-symmetric affine connection? And it turns out that now you're getting an infinitesimal group structure on the second order monad, sorry, I have to, it has to fall once, around every point P, okay? So you say, well, hang on, that maybe doesn't sound so nice like just infinitesimal affine second order. What is this that you have an infinitesimal group structure around every point P? Well, still an open question to turn that into an algebraic theory of which this is a model. I tried the obvious thing. I tried something that is called, that I would call like non-commutative affine combinations, but that has completely failed. So this is still an open question. Right. So as I promised, and this is basically just a listing of a few interesting results to kind of get you hooked, I can now go and forget about all this infinitesimal business. I can go into the category set, and I can start looking, what do I get there if I'm looking at the category of infinitesimal models of an algebraic theory, here again represented by a clone O. So it starts very nicely. It's locally finitely presentable. That's something we would expect. But then something interesting happens. I mean, as you might know, when I have a category of algebraic objects, they're not so awesome under co-limits. But here we actually get something really nice. We can glue these structures together. Okay, I'm thinking I'm running out of time, so I'm not going to be listing it all out, but just kind of pointing out this category, really beautiful. You basically take your algebraic models, you extend them to infinitesimal algebraic models, you preserve the limits, you preserve the quotients, like this is preserved on the embedding, but you get kind of these amazing gluing properties, which makes this kind of extended category like a category of spaces. So in some sense, this infinitesimal affine structure serves as a topology. So it's a nice intermediate between algebra and topology. Okay, let's end that here. Thank you.
Okay, thank you, Philip. Does anyone have questions? Can you catch this?
Hi, thanks for the talk. Pretty cool, a lot of stuff to absorb. This infinitesimalization of a theory, is there a sense in which this is like the free infinitesimalization of a theory? And if so, are there infinitesimal theories that are not brought about by that infinitesimalization?
Okay, thank you very much. That's an interesting question. I have not thought about that, so I kind of have no definite answer to that. I mean, it is an automatic construction that you can do. I guess, as always, if it's automatic, if you can formalize that, then it will have a universal property. But I'm not sure in which sense, because of course you have to add in the structure that you have the infinitesimal structure. You need to take that as an input. And essentially what is happening in the infinitesimalization, you have to restrict everything to partial operations rather than like global operations. That's what's happening. But in principle, and this is I think where it gets interesting, it could turn like any theory into kind of an infinitesimal version and kind of see what that gives you. But there's, again, still lots of things to work out. Thank you.
Okay, in order to stay on schedule, we'll have to move on, but ask Filip questions after the session. Thanks again, Filip.